Rational zeros theorem. Definition. Fp over q, so here's the formula, is a rational number written in lowest terms. And if p over q is a zero of f, a polynomial function with integer coefficients, then p is a factor of the constant term. So p here refers to the constant term, and q is a factor of the leading coefficient. So this is the first term, which is the coefficient of the first term, q, so it's leading coefficient. So quick example, simple one. Let's say you have f of x here equals x squared minus 2x plus 1. Our p here is here, the constant term, and our q is the leading coefficient, which is the first term, and in here it's x squared only. But if there's no number beside that, it is understood as you have a 1 here. So that 1 refers to the q. And then if you apply the formula p over q, you have 1 over 1. And this is always plus and minus because you have two possible signs here, plus and minus. 1 over 1, so it means that our possible zeros would be plus minus 1. So that's the answer. But if you want to really check if one of this or these two would be the real number zeros, you can use the remainder theorem. So let's try to check our positive 1 here. So plus 1. So we will have f of 1 equals 1 power 2 minus 2 times 1 plus 1. So that would be a 1 minus 2, that's a negative 1 plus 1, that would be a 0. So here's our remainder, 0. So it means the positive 1 here, it's the real number 0. We can check the negative 1. Okay, at the bottom, negative 1 here. That's f of negative 1 equals negative 1 power of 2 minus 2 times negative 1 plus 1. So the answer would be, that's our positive 1 plus 2, that's a 3, plus 1 is a 4. So the remainder here is not a 0, so it means the negative 1, it's not a 0 of the polynomial f of x. So I will label that negative 1 here is not a 0. Positive 1 here, it's a 0. So positive 1 is a 0. So only 1. So if you want to do it in a different way, you can apply the factor theorem. By factoring this out, you can see that the factors of x squared minus 2x plus 1 would be x minus 1 times x minus 1. So therefore, our root here, when you set this to 0, our root is x is equal to 1. Mm, Same thing with the other binomials, so they have the same value. So that's the proof that positive 1 is a 0. Okay, let's try another example. But note that when you're working with this rational zeros theorem, you're only asked to find the possible zeros. Okay, another example would be f of x equals x squared minus 2x minus 15. Okay, so let's label. So we have 1 here. That would be our q. Our 15 would be our p. So the formula would be p over q, and that's 15 over 1. And the possible factors of 15 would be 15 times 1. And then we have also 3 times 5 all over, for 1 that is a prime number, so 1 times 1. And then if you're going to list all the possible zeros, you pair like this. 15 divided by 1 is 15. So that's our first possible zeros. So possible zeros. Now when you see zeros, that's the roots, and another term for that would be the x-intercepts. So we've shown that in the previous section on how to find that by graphing and by remainder theorem and by synthetic division. So if your remainder is 0, then that k would be a 0 for that polynomial. So the first one is plus and minus 15. Okay, the next one would be a 1 divided by 1. So that's a 1. So that would be plus and minus 1. You can also pair 3 divided by 1. The other um, factor of the other number at the bottom, it's a 1. So we can use the same number 1. So 3 divided by 1, it's 3. So that should be plus and minus 3. And then the last pair would be 5 divided by 1. And you will have that as the possible zeros as well, plus and minus 5. Okay, so total of, if you're counting this is one pair, second, third, and fourth. You have 8 possible zeros because each of this group here has 2, plus 15, and the other one is negative 15. And that would be our answer for that problem, is just finding the possible zeros. Then if you want to test where's the real number zeros, um, by plugging in the value. Okay, so you can actually plug in each of these values to your f of x, and then if the remainder is 0, then that possible 0, it's really the 0 for that f of x. The same as I did in the previous example. Okay, so last example here. You're given with f of x. Let's try a higher power. You have 6x power 4 plus 7x cubed minus 12x squared minus 3x plus 2. Now, I have to mention also, same as the quadratic equation, we're looking at the degree of the equation. So the degree is the highest power, which is 4. That means we're looking at 4 possible zeros for this f of x. Okay. Sometimes within that 4 zeros, there will be real zeros and there will be complex zero also. So remember from the previous presentation, I said that you can graph this and you can find the x-intercepts. Those are the zeros of the f of x. If you try to count and it doesn't match to the degree of the f of x, it means that some of the zeros are imaginary zeros or complex zeros. So it's not going to be shown in the graph. Only the real number zeros will be on the graph. Okay, so let's label this. This is our Q here, and this is our P. Our formula is P over Q. So P is 2 over Q is 6. And then we have to have our factors. 2 times 1 for 2. At the bottom you have 6, 6 times 1. And then we have also 3 times 2. Okay, possible zeros. Okay, would be, let's mark that one. The first one is this, 2 over 6. So your answer would be plus and minus 2 over 6. You reduce that, that should be 1/3, right? Okay, and always plus and minus. And then you can pair 2 and 1 here. So that should be plus and minus 2. So that's 2 divided by 1. And then you can pair 2 and 3. That would be 2/3. So plus and minus 2/3. You can pair 2 and 2 here. So that would be plus and minus 1 because 2 divided by 2 is 1. And then the next pair would be 1 over 6. So 1 over 6 it's 1/6 plus and minus 1/6. And then try to pair 1 divided by 1 or 1 over 1. It's still a 1. We have already 1. And pairing 1 over 3, we have already 1/3. That's the first pair. And then we have the last pair, which is 1 over 2. That would be 1/2. And that's plus and minus 1/2. So counting the number of pairs here, 1, 2, 3, 4, 5, 6. So we have 6 times 2, that's 12. So we have 12 possible zeros here because you have the plus and minus there. Okay, so that would be our answer. Again, if you want to know which of these listed possible zeros are the real number zeros, you can actually use the remainder theorem. Plug this into the f of x. If the remainder is 0, that's your real number 0. If not, then that is not the real number 0. So rational zeros theorem is just try to narrow the number of possible zeros. So among those lists, you can actually find the real zeros by plugging in the values of those possible zeros one at a time.